Hello and welcome to our session, Firmware Security 101. Thank you for joining us. Thank you for taking the time to attend this session. A bit about myself to get started. My name is Slattery. I'm the CTO of Caribbean Solutions Lab. We are a cybersecurity provider based in the Cayman Islands, providing services throughout the English and Dutch Caribbean. I've been in cybersecurity for about 15 years now, including 5 years as a cybersecurity instructor. Taught around the Caribbean and North America as well. I've been in IT since in the dark ages, well before Windows 95. Why do I call it that? It's because Windows 95 really was the tipping point in the industry where computing became accessible to everyone, no longer the purview of specialty people in dark cloaks and back rooms and all that. In addition to being a cybersecurity for 5 years, I was also a cybersecurity contractor for the U.S. Army and held a secret clearance for a little while. So before we get started about firmware security, what is firmware? Firmware is nothing more than software code that runs inside chips, silicon chips. You're probably familiar with operating system software, application software. They're running on files on a hard drive. When you store that information in a chip with limited resources or memory or storage, you effectively get firmware. There are some crossovers. It is possible to put operating systems like Linux or Windows in firmware, so there's a bit of a blur in the lines there. But generally speaking, we're storing, the code sits in hardware rather than a file on a storage device, a hard drive, or a memory card or something like that. So where do we find firmware? Obvious places are computers. So in a typical computer, you have a BIOS, a basic input-output system, the chips that make the computer a computer as opposed to a paperweight. It's what sits between the hardware, hard drive, network card, etc., memory, processor that allow the operating system, loaded in files, to communicate with said hardware. What's what makes a Mac, makes a Windows machine, what makes a network card a network card. So firmware is found in pretty much everything in the computing world: firewalls, routers, network equipment, Bluetooth. There's chips inside a Bluetooth transmitter, but it needs some sort of low-level code that tells electrically how the computer to interact with the signal to make a transmission, for example. Firmware is found all over transportation, cars, airplanes, farm equipment, tractors, weather monitoring systems, satellites, Internet of Things. All these little smart devices, smart in quotes, that get plugged into the internet that call home. Doorbells, security cameras, fridges, microwaves. What else? Portable game consoles, for example. Firmware is also found in ATMs, cash registers, TVs. We mentioned that. Phones, of course, right? Phones have a certain amount of firmware built in, so what makes an iPhone versus an Android device of some kind, or Samsung, or whatever the case is. Medical equipment is common too. Pacemakers, insulin pumps, X-ray systems, pulse oxygen monitoring devices, industrial control systems, of course. Water, particularly common in utilities, so power systems, generator monitoring equipment, water systems, valve control, nuclear power plants. In essence, pretty much everywhere. Just think about it for a moment. What doesn't have an integrated circuit, a chip of some kind in this day and age? Very little. Even car engines now are very computerized. If you go back 25 years, you might get a car engine that's carbureted, doesn't do anything more than you tune the carburetor and that's it. It just runs and the spark plugs go. But nowadays, everything is computerized. So when we start talking about security, what are the big challenges with securing firmware? Well, the key thing to start is that it's typically sitting below an operating system. So we think in traditional computer terms, it's a chip that is required by the operating system to work. So how could the operating system necessarily know how to interact with the hardware without some drivers and connectivity and all that? So it is typically hidden by design. You don't necessarily want your operating system to be able to change firmware level settings. For example, it could alter the way a network card behaves, and that would be a security risk in its own right? We're often dealing with very specialized bits of chips or specialized functions as well. So they're designed to only do they're they're limited functionality, so they only monitor a water valve, for example. They know how to turn it on and off. They're not designed to run solitaire as well. They don't have the computing power or storage capacity, and even the architectural constraints of a full-on computer in that sense. Chips are often read-only. They're baked in figuratively these days, but they may not be modifiable. So, if there's a bit of code that has a vulnerability in the hardware and you have to replace it, that becomes a whole issue. Think about a good example of that are hotel door locks. There were vulnerabilities discovered or disclosed many years ago that required the entire industry to replace, or hotels to replace door locks across all their locations. So think about a hotel has 500 rooms, multiply that chain by 5,000 instances across the world, and there's a lot of locks to change in just one hotel chain, for example. Firmware can be rewritable or programmable, typically called PROM, programmable read-only memory, which is kind of oxymoronic or counterintuitive in that sense, but you can also erase it and reprogram it as well. You may be familiar with updating firmware in a computer or in an array controller or anything like that, a network device. Those things can be, with certain controls, rewritten. Other challenges are typically the delays between code testing and firmware protection. So, for example, if a network card manufacturer develops the firmware for a new 40 gig Ethernet card, for example, or a Wi-Fi adapter, they've done it, they've tested it, they bake it into the chips, and now they ship they contract the production of these chips. And if take a network card example, there are then millions and millions of chips produced for network cards, and when they ship, what happens 6 months later when they discover a flaw in it? Or they may not have tested a scenario, they may not have been able to foresee a particular scenario during original engineering that now has to be addressed. So there can be sometimes months, if not even years, between production and realization that something needs to be modified. Limited access to code, intellectual property conflicts. A lot of times these systems are very close, proprietary, so third parties going in and tinkering with it can be really concerning for intellectual property rights. If you were to steal the microcode for an iPhone, for example, and leak that, well then you're giving away almost in that example Apple's secret sauce to what makes an iPhone. And time and money, of course. That's the biggest challenge to almost any effort these days. If you look at that stat at the bottom, in the next couple of years, there's an estimated 75 billion IoT devices. Mentioned IoT, Internet of Things, but let's just talk about interconnected things. Something you don't have to be connected to the internet to have communications. You can be closed inside a power plant or inside a vehicle or something like that. But those are still devices with firmware that we need to manage, have visibility on, and sometimes update. So, some quick examples of firmware attacks. Now, in 2008 was the configure worm. Now, I cite this example because it kind of blurs the line between firmware and software in that sense. But configure was a Windows worm that exploited vulnerability that spread around the world and leveraged some very interesting techniques. Read about that separately. But in one instance we are aware of that we worked with a healthcare organization, they actually had X-ray management systems, so the control systems that did imaging, and they were built upon Windows XP, but that was embedded in firmware. And the problem there was it's still Windows. It was in read-only memory, but what happened was it was a vulnerable version, and the configure worm kept on infecting the X-ray machines. And the only way to clear it, because it was read-only, they couldn't install antivirus on it, was to reboot the machine. It took a long time, and I don't recall the full. I think they eventually replaced the systems, but there was no real way to protect those systems from reinfection. A great example of firmware attacks would be the Stuxnet worm, which specifically targeted the control systems around Iranian nuclear fuel enrichment centrifuges. So that actually was running on Windows. It traversed USB keys, things like that, air-gapped networks. But the point was, it was directed at the control systems of industrial equipment. 2014 was an interesting one. 100,000 fridges and other home appliances were hacked to perform spam attacks. So basically, all the 100K fridges and home appliances that had that were internet connected were then taking part in massive spam campaigns. Around that same time, I recall an interesting one. There was an iron manufacturer, or it was discovered that some brand X of iron shipped from, I don't know, it was Asia somewhere, actually had embedded and hidden Wi-Fi clients. So yes, this little iron that was designed to press your clothes actually was joining public and unsecured Wi-Fi networks to participate in bot and spam attacks. 2015, IBM researchers did a proof of concept attack against Jeep CAN bus. CAN bus is a controller area network. It's actually used very commonly in aviation and transportation vehicles. It's a way for many devices internal to a system to communicate back and forth. And they were able to plug into the CAN bus via an adapter. They're very commonly found in the industrial world, and take control of a full vehicle. And now think about the risks of, that's just a Jeep, but what about a remote autonomous vehicle, or an autonomous vehicle, or a train, or plane, or boat? You can see where some of the risks come from that. 2016 was an interesting one. It was a DDoS attack. At the time, one of the largest of its kind, and it was a Mirai botnet that also came out of firmware bot clients. And recently, there was an interesting one, Moonbounce malware, that actually sits inside your computer's BIOS. And even if you were to reformat your hard drive, because it's sitting below the operating system, it actually just reinfects your computer. You may have heard discussions about what are called rootkits. They were early versions of these computer firmware attacks. The idea being it rooted your system, it hid below your operating system. They're still present, and they're kind of seeing a bit of a resurgence as threat actors just find more and novel ways of circumventing our security. The old adage of build a better mousetrap, you get a smarter mouse. It's the same in the cybersecurity defense industry as well. You build better defenses, the attackers get smarter. Wash, rinse, repeat. So some basics of firmware security. This is not a comprehensive list. This is just some ways, some techniques and ways you can do a better job of securing your firmware and your other network interconnected systems. So first thing to do is cover your assets. If you don't know what's plugged into your environment, you can't control it, you can't manage it, you can't protect it, you can't do anything about it. You've got to know what's there. So fundamental in almost any cybersecurity efforts is knowing your inventory. So just understanding what's there. Hopefully, if you're a smallish organization with 100 devices, webcams, printers, faxes, copiers, smart doors, etc., then that's probably okay. If you're looking at a large university, for example, with 100,000 endpoints of just interconnected devices, that's a different story. Manual inventory tracking, of course, is one method, but obviously for any larger for any scale, you're going to need automation, and that's the key thing there. Also, you can often find inventory asset information coming out of third-party tools. For example, you may have a VPN system that allows you to track devices plugging in. That it might tell you that you've got more, phones connected or other devices connecting that you weren't aware of. Application management might be able to tell you that as well. So look for out-of-the-box ways of obtaining inventory. Your network, of course, is a great way. So if you have managed network or network management tools, you can grab that to find out what's plugging in. I think there was a stat that SANS released a number of years ago that said, the average person, this is probably 10 plus, that the average household has 2.5 devices per person. I think nowadays it's probably closer to 4. So especially in campus environments, you have one student, you might have 4 devices: a laptop, a tablet, a phone, a gaming console, what have you. So odds are you'll find that there are a lot more devices in practice than you expect at a given time. So once you know about what's plugged in, you can start tackling, or what's connected to your network, you can start tackling how to protect it. One of the first things you can do is perform vulnerability management, understand what's there, have a thorough understanding of the risk, the vulnerabilities in a given system. Hopefully, you don't have too many vendors and models to deal with. Again, automation is the key. But one catch there is, of course, you can't always scan, or you may, if you're dealing with Windows systems or printer or webcam, those are fairly commonly found. You can probably find good vulnerability information on them. But if you're dealing with a door control or a water pump management system or something like that, that might not be so common to find out, the latest vulnerabilities of a particular control device or a power station tool or something like that. So that is a challenge to worry about. So what you can do there, get to that point in a second. So hardening is another thing you can do. Most devices have default passwords, default services, so definitely worth being able to remove default passwords, change the passwords, remove accounts and services. A couple of years back, during the craze of smart doorbells, you probably remember all the issues around the news around, I think it was Ring, I'm not going to pick on them, but brand X of smart doorbells that had default passwords. People's videos were leaking to the internet. Baby monitors as well had an issue where they became so easy to use that they just plugged in and opened up all the ports, and you had numerous stories of strangers connecting to particularly two-way baby monitors and speaking to kids randomly across the internet. So closing those network ports, locking it down, very, very important. You can, in certain situations, implement host controls like antivirus, intrusion prevention, application control, and that only typically works if you have something that's like a Windows embedded system, where you actually have an operating system, Linux maybe, that you could install and applications on. Again, we're often dealing with small dedicated devices that only do one function or limited functions, control a valve, control a pump. So that becomes a problem. You're not going to install an antivirus on a smart door lock, for example. It's just not going to have the capacity for it, and wrong architecture. Final point there is, if you can, build and have the conversation around security and vulnerability management as you're investing, designing your interconnected devices infrastructure and purchasing. It's so much easier if you can build that in ahead of time. So instead of just buying whatever looks good, you make a concerted effort to vet the vendors, find one that's got a good reputation, for example, and then look to buy a consistent base of systems. Rather than buying maybe out of 1,000 devices, you can limit yourself to one brand and two models, rather than dealing with potentially 20, 30, 40 different models, which would make your life much harder to deal with down the line. So then we get to network control. So if you've exhausted all the possibilities of hardening and protecting the hosts, the logical place is at the network, right? Where they connect to, whether it be internally or to the internet, doesn't really matter. Network's a network. Just where it goes is another story. One of the first things you can do is isolate the network. So imagine you had a bunch of webcams that you can't do anything with. They are what they are. So you've got them plugged in. Well, if you put them on their own dedicated network, your perimeter control rules, for example, your firewall rules that isolate the webcam network or pump network or whatever the control system network is from the rest of the network or the internet, you can now create firewall rules that specifically protect and limit who can access those functions. So instead of just having a free-for-all where anyone can connect to any device, you've now restricted it down to specifically what's needed for those systems to function. A great recommendation is segment based upon function or vendor. So it means splitting your network out depending on the function. You can think of it as segmenting based upon risk. The idea there is if you put all your X-ray machines, to use a healthcare analogy, on one network, your transfusion monitoring machines on another network, you can now, again, it makes it easier to create those firewall rules, to make those to add those controls, to monitor what's going on those networks. And you can do a much easier job securing it too, for example, if or reacting to a threat. So if there's a threat that's making a way around X-ray systems, for example, you can quickly lock down those network ports, for example, and not impact the rest of the organization, not impact the rest of the devices. When considering network controls, another great way is to add a layer of security independent to what you already have to protect that network. So we do this quite commonly with SCADA industrial control systems, particularly with utilities. They may have a firewall brand X. We'll add in an independent network security device just inside that perimeter Now, that perimeter doesn't mean it's to the internet. It could also be to internal systems. But it's important to separate that out. So the control systems have the standard protection rules, and then a device sitting on the inside that will do its own set of inspection and protection mechanisms. It's the principle of layered security. It's having at least two independent layered controls to protect a given part of the organization. So it's not all doom and gloom. There have been some very notable security efforts in firmware over the years. Intel, being a rather large chip manufacturer, has actually been making efforts for a long while. I think, give or take a decade plus so ago, they had actually started building in security functions and capabilities into their chipsets that support the Intel platform. It was up to the vendors and manufacturers and software to take advantage of it. One of the early ones I recall that we used as well was a cryptographic module that offloaded drive encryption to make it faster. So historically, again, a decade plus ago, encryption, which is a fairly CPU intensive effort process, was being handled by software. If you had the right Intel based system, those computational efforts were actually offloaded to the hardware, making your user experience that much better. That's still carried over. They still have those functions, but it's evolved now into the Trusted Platform Module, or TPM. If anyone of you have been looking at Windows 11, you've probably seen the requirements of Windows now wanting a TPM, I think version 2 module, whatever it is. It's a great step. Windows and Microsoft has finally started taking consciously thinking about security, or at least appears to be. And so by requiring the TPM module, they can enhance the capabilities of the Windows operating system for better management, better encryption performance, better asset management. So one of the interesting things you can do with the TPM is it cryptographically proves and tracks every device on your computer. And the idea being is if for example, your hard drive were stolen or cloned out of your system, it would be difficult, not impossible, but very difficult for someone to boot it up, because it would recognize it's a different piece of hardware. You needed to go through a couple steps to validate this was an authorized process or action. Trapezoid 5, they were an early adopter or entry into this space. They actually use TPM modules, particularly in server farms and data centers, to cryptographically prove or disprove where a virtual machine or where an operating system is actually running. So they could be able to prove, for compliance reasons and everything else, that this firmware has not been tampered with. There's a whole management process to track that and alert you to if, for example, a workload in a highly virtualized environment were moved to an untrusted host. We could set up alarms and take action, shut down the system, lock it down, for example, things like that. NetRise is also an interesting player in this space. They take firmware and vulnerability management to another level. We mentioned earlier how a lot of firmware devices, right, printers, faxes, x-ray machines, insulin pumps, what have you, they're not exactly common that you can go buy at Best Buy where people are tinkering with all the time. So what NetRise has done is that they've taken on themselves to catalog many firmware vendors and manufacturers, device manufacturers, and start tracking what vulnerabilities are disclosed, and they'll assist you in that effort of, explaining, understanding your inventory, then disclosing what's vulnerable, how you could protect it from threats and all that. So some good examples there. So call to action. So what can you do with all this information? Mentioned earlier, the best thing you do is know your assets, get to know them, understand what's plugged in. And this is something you can actually also do at home as an exercise for yourself. We actually recommend it. I did a LinkedIn post last Christmas about people buying all these new devices and things, but when you're plugging it at home, it's far too easy in the world of particularly consumer devices, electronics, to sell a device and enable convenience over security or privacy. The example I cited earlier about Ring cameras and baby monitors and all that, where they just made it so easy to plug in and get going that no one was changing the passwords. Ports were left wide open. So at home, you can do all this yourself to get a better understanding of what's happening. Understand what's plugged into your network, build that inventory, look at the firmware, what needs to be updated. There was another case not too long ago of QNAP network attached storage devices. Really popular. We've got a couple. Really beneficial. They had this habit. We don't use it. We've never liked it, but that we could just plug it in and have it access your files over the internet. In the Caribbean, accessing those telco links are too expensive, too slow anyway. But the principle, I can see why it might be interesting to have access to your files from anywhere in the world. But the default security was a little lax, and what happened over time too is there were vulnerabilities, and as a result, they were being abused to have ransomware actually installed on the devices themselves. So yes, little network attached storage devices were getting ransomware, and that was that, because they were just too easily plugged in and connected to the internet. So updating firmware, that was the first kind of a response that was, well, initially it was, disconnect, download the firmware offline, update it, harden the system, isolate them as well. In that example of the QNAP device, do you really need it accessing the internet? Maybe, maybe not. But some of the things you can do is, build that. Most home wireless devices, routers, have the ability to create separate networks. So, for example, your smart doorbell doesn't need to be on the same network as your computer that you might do, shopping and banking on, for example. You have webcams that, if you want to access it from the internet, that's great. Build another wireless access point, a wireless network just for that, so it's separated out. There are also options in most wireless routers to limit what can connect to each other. So it kind of depends on manufacturer, so you have to look at the manual of your device. But by default, a good device should limit the ability for one device on the wireless network to talk to another. Sometimes for convenience that gets turned off. But you really should have that turned on whenever possible. I mentioned also guest devices. If you have people visiting, and if they are truly just visiting someone's phone and whatever else, it's important to just separate those out if possible. The analogy of wireless guest devices and all that. I mean, if you would go back a few years before wireless was ubiquitous, you would think twice about just having someone randomly walk by, particularly in retail, and just plug in their laptop to your network. If someone walked up and you were running a shop and they said, "Hey, you don't know me, but would you mind if I just plug in my laptop to your network for a little bit? It'll be fine. I won't do anything." You probably most likely would think twice, right? But now with Wi-Fi, particularly public Wi-Fi, that's a huge risk. I'll share one last story of Comcast in Southwest Florida. I don't know if they did it anywhere else. They actually turned all their cable modems with Wi-Fi boxes into a public mesh network. The idea being, I personally had huge issues with this. Basically, if you had a neighborhood that had Comcast cable modems, there then became this massive neighborhood of free Wi-Fi, and if you moved around the neighborhood with your phone or laptop, you were actually jumping across the access points across all these private homes. They turned every private installation into a public hotspot. It sounds benign. It was I see why they'd want to enable that. If it's another selling point for Comcast to have this almost nationwide free Wi-Fi. But the problem was a lot of organizations, let's pick on banks, for example, when they see malicious traffic coming from an IP address, they'll typically block it for a certain amount of time. Well, what happens when someone maliciously does something and they happen to be on your home network at the time? You now get blocked. And I've actually dealt with this personally in an instance where we needed the bank wasn't helping out. They were just saying, we've detected overtly malicious traffic from your connection. You got to call a specialist to take care of it. Realized what was going on, rebooted it, got a new public IP, and it was fine. But the point there is, it sounds great, that convenience is great, but there are real risks and implications to that. So with that, that's the end. I appreciate your time. If you have any questions, feel free to reach out to me. Those are my mobile phones, so be kind. Probably best to text first or WhatsApp, but happy to answer any questions, and I thank you for your time.